So hello everybody, in this lecture we are dealing with a very interesting concept and the concept which we are discussing is regarded as toppling. So when I refer to something as the case of toppling, so what does it actually imply? So there are different terms that are used for it. That is, sometimes it is says that the block tip over the surface. So that is also hinting towards the concept of toppling. So let us understand over here with the help of an example of a bottle. So if I apply a certain force at a point on the bottle, it will translate. So we already understand this concept that F is equal to ma. A force is applied on the block and it is accelerating with a certain value. If there is a friction involved, so our equation will become the applied force minus the value of frictional force is equal to ma. And today we are discussing the concept of toppling. That is, if the surface is sufficiently rough, kindly understand this point. I'm emphasizing on this throughout the concept of toppling. We will be emphasizing on this fact that if the surface is sufficiently rough and a force is applied at a certain point, then instead of translating, so we are seeing that the block is tipping over this point and then it falls. Let me repeat this one more time over here again. So we are putting the block over here in a place and then a force is applied. So if I withdraw the force now, the block will come back to its position like this. But if I exert a force till a certain point and then drop, the block will definitely tip over that particular point. So that will become the axis of rotation and the entire system will fall on the other side. This is regarded as toppling. So let us understand the concept over here as to how exactly toppling happened. So if I begin over here in this way, so let me first of all construct a horizontal line. So I'm constructing a large horizontal line for all the different instances that we will be discussing over here. And now I'm considering a block. So in the first case, I'm considering a block like this. Like this. And now I'm saying that a force F is applied. The surface is sufficiently rough so as to prevent any type of translation motion that may happen. I'm again emphasizing on this fact, the surface is sufficiently rough to prevent translatory motion for the time being. And now a force, if it is applied. So now what will happen if I draw the FBD of the block at this instant? So the weight mg is acting in this direction. And a normal reaction force is acting on the block like this in this particular direction. Just before the force F is applied. Just before the force F is applied. Now, after a certain instant of time, the block will look like this. And if I draw its FBD, so the weight mg is acting in this direction. And this is the point of pivot, yeah, instantaneous axis of rotation for this particular system, about which this entire system is rotating. About which this entire system is rotating, and a force F is continuously being applied over there. So what are we seeing is that the weight mg starts shifting towards the instantaneous axis of rotation. And suppose if I withdraw the force at this instant, if I withdraw the force at this instant, so what will happen if I withdraw this force at this particular instant of time? So the weight mg will produce a torque in the opposite sense, and the block will fall back to its initial position. The block will fall back to its initial position that was happening in this case like this. So I'm applying a certain force. If I withdraw the force at this instant, if I withdraw the force at this instant, it comes back to its original position. Why? It happens because of the fact that the weight component is again bringing the block back to its position. But if the force is applied for a considerable span of time, such that a position like this is reached. The force is applied for a considerable span of time such that we reach a position like this where the weight mg is acting at the instantaneous axis of rotation. So just beyond this point, what will happen? Just beyond this point, just beyond this particular point, the weight will start acting on the other side. The weight will start acting on the other side, and the system will eventually topple on the other side. So the toppling will become successful. So over here, if I exert this force for a considerable angle, that is at this point, maybe a little more, and even if I withdraw the force at that point, the weight component which is acting on the other side will topple the system about that particular axis of rotation. So this is the first thing which must be kept in mind, that there is a weight which is acting in the downward direction. There is a point of instantaneous axis of rotation, or the point of pivot, about which the entire system will start rotating, and as a result of which, after a considerable span of time, if you just withdraw the force, if we apply the force and withdraw the force, it will fall back at its place. But if the force is applied for a considerable span of time, such that the weight crosses the instantaneous axis of rotation mark. This is very important concept over here, such that the weight crosses the instantaneous axis of rotation mark, the toppling will successfully take place. So over here, what we are exactly doing is, so let us consider a scenario over here like this, where we are finding the H required for toppling to take place, and I am considering a block over here like this of a certain dimension, a particular height. So over here, if I draw the FBD of the block, so the weight of the block mg is acting in the downward direction. The system will begin to topple about this particular axis of rotation. This becomes the instantaneous axis of rotation. A force F is applied over here at this particular point, which is at a height h from the rough surface, and over here, if I consider this dimension as a, so this will become a by 2, where the entire weight is acting. So this is the thing which we are saying, and we are saying that the surface is sufficiently rough. So if I say surface is sufficiently rough, so I can say over here that the normal reaction force which is going to act is mg, and the corresponding value of frictional force is going to be mu mg. So we say that the force applied is less than equal to mu mg. So there is no translation possible. Translation is not possible. Or I can say that the surface is sufficiently rough. So we are considering a case like this. So over here, for toppling to take place, for the system to topple, it is required that the torque produced by the applied force is greater than the torque produced by the weight mg. So the torque produced by the applied force will be in the clockwise sense, and the torque produced by the weight will be in the anti-clockwise sense. So if the torque produced by the applied force will become greater than the torque produced by the weight mg, so over here one more question can be asked: why are we not considering the torque produced by the normal reaction force? So this must be noted over here, that when the system starts to topple, the normal reaction force will act on the instantaneous axis of rotation mark. So now the R cross F value, so now the force is acting at the axis of rotation. So if the force is acting on the axis of rotation, so it is not going to produce any torque effect. So that is why we are not considering the effect of the torque produced by the normal reaction force, because when the system starts toppling, the torque, the normal reaction force is acting on the instantaneous axis of rotation mark and will not produce any torque. So over here we say that if the torque produced by the applied force just becomes greater than mg. So we are solving the case of equality. So over here I can write that F into H is just greater than equal to mg into a by 2. Mg into a by 2. So over here we get H is greater than equal to mg a upon 2f. Mg a upon 2f. So the minimum height for toppling can be written as, so H must be greater than equal to, so we are taking the sign of equality. The minimum for toppling will become twice of F, can be written as mu mg. So we are applying, the force must be less than equal to this. So we are applying the maximum value of force. So if this is maximum, this value will be minimum. So we are calculating the minimum height for toppling. That is, we have put the maximum value of force to calculate H minimum. So over here we can cut mg, we are left with a by 2 mu. So this is the minimum height for toppling to take place. Again, I am repeating this aspect. The surface is sufficiently rough and the force is applied, as a result of which the toppling will start taking place about the instantaneous axis of rotation mark, and the system will topple like this. So this is the minimum height requirement for toppling to take place. Let us move to the another application for the toppling. Another application for toppling. So this time we are taking a question like this. So we are considering an example of a equilateral prism. We are taking example of a equilateral prism which is resting on a sufficiently rough surface, which is resting on a sufficiently rough surface, and a tangential force F is applied at the top of the prism, whose side dimensions are equal to A. It is an example of an equilateral prism. So find the minimum value of force needed for toppling to take place. The minimum value of force needed to toppling to take place. We are solving this particular case. So over here we begin with this concept back again, that the weight of the prism is going to act in the downward direction from its center. That is, this is the point where this entire weight is acting, and this is becoming the point of instantaneous axis of rotation. This is the point of instantaneous axis of rotation about which the entire prism system will topple. That is, this time we are applying a force like this. So it is toppling about this particular point. So it is tipping about this particular point. This becomes the instantaneous axis of rotation about which the system is toppling. So this separation is a by 2. And if I calculate the vertical height, then it is going to become root 3a by 2. You can solve it in various ways. So this angle is 60 degree. And if I wish to calculate the height, it will be a sine 60 degree. That is root 3a by 2. So now if we apply the force equation, so the force equation requirement is simple, that the torque produced by the applied force is greater than the torque produced by the weight. So the toppling will take place. So if we go with this particular aspect, so I can say that the torque produced by the applied force is just greater than equal to the torque produced by the weight mg. So we will solve for equality. We are solving for equality. That is F into root 3a by 2 is equal to mg into a by 2. So the weight mg is acting at a distance of a by 2 and the force is applied at a height of root 3a by 2. So over here I can solve easily that the force requirement is equal to mg by root 3. So if this particular force is applied such that the surface is sufficiently rough, I am again repeating, the surface is sufficiently rough, so the system will topple about this particular point. and the system will be rotating about the marked instantaneous axis of rotation. We are taking another application over here. So in the another application, I am taking example of toppling in case of an inclined plane. So we are taking example of toppling on an inclined plane. So on an inclined plane, we are considering the following cases. So let us first of all take the case of a cubical block. So I am slowly increasing the angle of incline. So initially this is the angle of incline, and then we are taking this particular angle of inclination. So over here I am drawing a block, not like this. So I'm drawing a block over here. Again, the surface is sufficiently rough, and the problem that is asked is calculate the angle theta of the inclined plane. Calculate the angle theta of the inclined plane so that the cubical block will tip because of its own weight. Will tip because of its own weight. So this is the problem that is being asked over here. So over here, if we mark the instantaneous axis of rotation mark, the surface is sufficiently rough. I'm again telling you this. The surface is sufficiently rough. So this becomes the instantaneous axis of rotation mark. So at any angle, which is not the angle at which the toppling is going to take place, the weight mg is going to act towards the left of the instantaneous axis of rotation. So as a result of which I can say that the toppling will not be possible because of its own weight. The toppling will not be possible because of its own weight. The system will topple only when the weight crosses the instantaneous axis of rotation mark. Again, we are back to this first slide where the toppling happened when the weight crosses the instantaneous axis of rotation mark. The system starts toppling. So if we have to write the maximum value of angle theta or the maximum angle of inclination possible for the inclined plane so that system do not topple, we will solve for this particular case. So if we are solving for this particular scenario over here, so I am drawing another diagram over here where I am saying that the weight mg is acting in this direction. The weight mg is acting in this direction, and this is going to be our cubical block. This is going to be our cubical block. So just after this angle, the weight will cross the instantaneous axis of rotation mark and the system will topple. The weight will cross the instantaneous axis of rotation mark and the system will topple. So if we apply equation over here, so at this particular instant, the normal reaction force is just balanced by the instantaneous axis of rotation mark. And over here, if I consider something like this, so this angle is given to us as theta. This is 90 minus theta, this is theta. And I'm marking this angle as alpha. So the center of mass is at a height a by 2 from the base of the cubical container. And this this base length is also a by 2. So if I consider this particular triangle over here, so this is a by 2, this is another a by 2, and this is the angle alpha, such that tan alpha is turning out to be 1. A by 2 upon a by 2 is turning out to be 1. And over here I can write that alpha plus 90 plus theta is equal to 180 degree. So alpha can be written as 90 minus theta. And hence I can write that tan of 90 minus theta is equal to 1, or cot theta is equal to 1, that is theta equal to 45 degree. So if a cubical block is placed on an inclined plane, then it will tip because of its own weight at 45 degree angle, of inclination. of the inclination of the incline, that it will tip without commencing sliding, such that the surface is sufficiently rough. Over here, I mean to say that the angle of repose must not be reached, otherwise the block will start sliding before tipping itself. So in order to tip, the coefficient of friction must be strong enough, that is, it must be greater than the value of tan inverse mu must be greater than tan inverse, that is 45 degree value 1, mu must be greater than 1. So if we place a cubical block over there in such a scenario, so it will tip at 45-degree angle. In the similar way, let us take an example of a solid cone, and we should determine the concept again for the same angle theta for a solid cone. So when, at what angle will the solid cone tip over? So I'm not drawing two diagrams this time. I'm drawing straight away one single diagram. Drawing one single diagram. So over here we know that the system will tip. The system will tip when the weight is acting at the instantaneous axis of rotation mark. When the weight is acting at the instantaneous axis of rotation mark. So this is instantaneous axis of rotation mark, and it is an example of a solid cone. So I can say that the center of mass is at h by 4 height. The center of mass is at h by 4 height. So if h is the total height of the cone, so it is h by 4 height, and this is radius of the cone. This is a radius of the cone, such that the weight is acting like this on the instantaneous axis of rotation bar. The weight is acting on the instantaneous axis of rotation bar. So just after this angle, the weight will cross the instantaneous axis of rotation mark, and the solid cone will topple because of its own weight. It will topple because of its own weight. So if we are solving for this case, then we say that this particular angle be marked as alpha. This is the point where the normal reaction force N is acting. This angle be theta. This is 90 minus theta, and again we have this angle as theta. This is 90 degree. So again I can write from here that tan alpha is equal to h by 4r, and alpha can be written as 90 minus theta. So I can write cot theta is equal to h by 4r, or theta is equal to cot inverse of h by 4r. So for this particular angle of inclination, of the inclined plane, a solid cone placed on a sufficiently rough inclined plane will tip because of its own weight. It will tip because of its own weight for this particular scenario. Next, we are dealing with one interesting problem. So again, I'm moving towards another application of toppling. So we have taken the case of turning of a car on a circular road. For taking the consideration, what if the car topples? So we haven't taken that into consideration as the toppling of the car. So what we have done so far, so I'm just giving you a quick recap. So let us initiate with the recap of turning of a car on a circular road. Turning of a car on a circular road. So if we begin with this particular concept, so let us consider this circular road like this. So we are considering a circular road like this, and we are making a car over here. So may not be a good looking car, but from the perspective of physics, it is a very nice car. So this is the car which I am drawing, and it is moving with a speed v. Moving with a speed v on a circular turning of radius r. So now to prevent, we are considering only the case where we are not considering the height of the vehicle, the length of the vehicle. We are simply considering that aspect which we have already learned. That is, a force mv square by r will act in this direction, and a frictional force must act in this direction so as to prevent the car from falling on the other side of the circular track. So over here I am writing to prevent slipping. To prevent slipping, it is important that mv square by r is less than mu mg, less than equal to mu mg. And over here I get that the velocity requirement is equal to, so we take the maximum requirement, that is the maximum permissible velocity. So we are getting value equal to root over mu rg. So this is the maximum permissible velocity so as to prevent slipping while taking a circular turn by a car. But if you take into this consideration that there is a possibility that the system can topple as well. And you must have seen it in quite a movies where it is shown that while taking a turn, the car turns over that particular wheel and it starts falling into the the khai, or say the mountain top. It starts falling down from there, and the protagonist of the movie dies. So let's not get carried away in that manner. So over here, we are trying to understand what will happen to prevent toppling. And let me give you one more observation. If you look at the racing cars, you will find that those cars do not have much height. Those cars are very short. And it is for the same reason that those cars are very short, to prevent toppling of the car. To prevent toppling of the car so that it can reach a high velocity without tipping over one particular wheel. So if I draw a more extensive diagram for this particular car, so I'm drawing the car in a way like this. So I'm drawing the car in a way like this. So this is the back view of the car, which we are seeing. The back view of the car which we are seeing. And over here, I consider that the force which we are talking about, that is mv square by r is acting at a height h. So it is acting at a height h. And because of this force which is acting on the circular turn, the system will topple about this particular wheel. The system will topple about this left wheel. So if I draw the normal reaction forces, so what will happen? This wheel at the time of tipping, at just when the velocity is reached of tipping, this wheel will become the instantaneous axis of rotation along with the wheel on the front edge. That is, this car will topple like this about these two wheels, and the inner wheels over here will get lifted off, and the condition will reach only when the weight mg of the car which is acting in the downward direction, such that this is the length of the car. So we are taking this as L by 2. This as another L by 2. This is the length of the car. So the system will tip. The system will tip if this torque is more than the weight mg. Is more than the weight mg. The system will tip if mv square by r produces more torque in comparison to the torque produced by the weight of the car. and hence I can write about instantaneous axis of rotation. About instantaneous axis of rotation, so I can write an equation like this, that mv square by r into height h is equal to mg into L by 2. mg into L by 2. So we are taking a case of equality, that is this must become greater than equal to this. So after this it will definitely tip over. So if we solve for this, we get this value as v is equal to rgl by 2h square root. So this is the velocity at which the toppling will take place. This is the velocity at which the toppling will take place. So whichever of these two velocities, that is mu rg, root over mu rg or root over rg by 2h is greater. So the car must not cross that permissible velocity. That is, there is a possibility that the car may topple rather than sliding off the circular road, which will become more fatal. So both these possibilities must be kept in mind. So this is based on the design of the car, and that is the reason I was saying that the height of the car, of the racing cars, are made very less. So if you reduce the value of this height h, so this velocity will increase. So that is, the car can go with a much greater velocity without tipping over while taking a circular turn. So these are the concepts along with the application which we have read about toppling.